All right, today guys, we're going to be talking about stoichiometry. And you guys, stoichiometry is a technique we use in order to often predict how much product we'll produce in a chemical reaction. So guys, this is going to be a review for a lot of you guys, hopefully a review for all you guys, most of you guys, but then there'll be maybe one or two some new things here. It says, I feel sorry for people who lived before smartphones. All they had to amuse themselves was 197 million square miles of the real world, but these guys are really living on their smartphones. Law of conservation of mass, basically, you end up with what you start with. You don't end up with the same type of matter, but you end up with the same amount of matter. I'm going to kind of read all that. You guys, chemical equations you should be familiar with. We're going to see from that, but this is like a kind of a structural images of, here, we'll show what it is. We have CH4, you guys should remember what that is. Methane, you guys remember that's the same gas that comes out of our Bunsen burners here at the lab, which we shall be returning to here shortly. So you guys know methane is combustible. What does that mean? It's going to react with oxygen in a combustion type reaction. Methane reacts with oxygen. You guys remember what's often the byproducts of the combustion of hydrocarbons? Carbon dioxide and water. It's a pretty simple scenario. Now you would think, why isn't that the case when we have cars? Because you have pollution, you have other things besides hydrocarbons and gasoline that gives off the pollution and so forth. So anyways, what you'll see, for example, one methane molecule will react with two oxygen molecules in order to produce one molecule of carbon dioxide and two molecules of water. What you guys should notice is the same number and type of atoms that we start with are the same number and types of atoms that we end with. The reactants appear on the left. Once again, this is a review for a lot of you guys. Like, yeah, I already know this. This is good. Okay, you should know this. We start with the reactants, and then we produce the products. The products are on the right side. Once again, you can also indicate the states of matter. Sometimes that's not included, but oftentimes it is. And in this case, we're dealing with all gases. Coefficients, those tell you the number, right? Remember, we use those in order to balance the number of atoms, and you can see two oxygen molecules, two water molecules. That's what allows for all of the atoms to balance on the reactant side and product side. And then we got the subscripts. You guys know H2O. That just means there's two hydrogen for every one oxygen. That I think we know. Just sitting there drinking, watching TV. Didn't you hire a life coach? Yeah, he benched me. Okay, so he didn't really make it in life. That's not going to be you guys. You guys are going to get develop big old buff beefy brains, and you guys are going to do something with yourselves. Formula weights. You guys, we talked a little bit about this, I think, in a previous video lesson. Formula weight is kind of it's like we might call it a molecular weight, but when we're referring to ionic compounds, we don't call them molecules, so we'd say formula weight. So if you had to get the formula weight of calcium chloride, I think you guys already would know this. You look up on the periodic table, you'd see the molar mass of calcium is 40.1. The mass of chlorine is 35.5, but since it's CaCl2, there's one calcium for every two chlorines. We're going to take the mass of chlorine and multiply it by 2, then we get the totals here, and then we add them up for the overall formula weight for calcium chloride. Once again, they call it a formula weight. When you're dealing with an ionic compound, you remember how you tell ionic? If you have a metal and a non-metal, we call it formula weight. If it was with a molecule, we call it molecular weight. But this is something that should look familiar to you guys. Molecular weight, and you guys remember, usually when we're dealing with molecules, you're going to be dealing with non-metals, right? So here would be a typical molecule, ethane, C2H6. Once again, if we were to get the molecular weight, we take the AMU weight of carbon, which is 12, but we multiply it by 2 since there's 2 carbon atoms, and hydrogen, you guys remember, is 1. And you guys, that's what I'm going to have you guys do when it comes to the periodic table. You guys look at your typical periodic table, it's going to go to like the thousandth or the 10,000th place, like 0.00 whatever. And technically you're supposed to use all those values because those were experimentally determined. But what we're going to do is to make life a little easier, we'll try to round to the 10th place. Okay, so that's what we'll do. And then you just add those all up, and so the molecular weight of ethane is 30.0. If you need to find the percent composition, like we want to see of a particular compound, how much of it is a particular, what's the percent of a particular element. And you guys know percent's pretty easy. Percent is just a part over a whole. If we're dealing with a compound, what's the part we're interested in? That would be the element. What's the whole? That would be the compound. You see, it's always the part over the whole, the weight of the element over the weight of the compound, and then to get a percent, we multiply by 100. So if I wanted to figure out what percent carbon, let's say we have ethane, I want to know what percent of ethane is carbon. So of all of ethane's weight, what percentage of it is due to carbon? Well, just kind of start us off, what do you guys think is going to contribute more to the weight of ethane? Carbon or hydrogen? Somebody might say hydrogen because, well, Mr. Willison, there's 6 hydrogens, but you got to realize hydrogens are very light, right? They only weigh 1 AMU, whereas a carbon atom weighs 12 AMU. Each carbon atom is 12 times heavier than a hydrogen atom. So even though there's more hydrogen atoms in an ethane molecule, in any given sample of ethane, the majority of the weight is going to be due to carbon. And so we would just use our simple formula here, the weight of the element over the weight of the compound. The weight of the element, you guys see, carbon weighs 12 and there was 2 of them, so that would be 24. I take the weight of the element over the whole, which is the compound, which if I added up all those from before, from the previous slide was 30. 24 of 30 times 100 is 80%. So any ethane sample you have, 80% of it is going to be, by weight, is going to be due to carbon. It says conventional halos were replaced when Walmart bought us out, so they gave them a little barcode instead of the halos. All right. Mold. You guys, this is so fundamental to chemistry. I wanted to do this again. You guys, in fact, I'm going to do the exact same lecture, but what you guys are going to find, you who've already had me before, here in AP, you guys, we're probably by the 3rd or 4th lesson so far. We're pretty much about 5-6 weeks into a regular or honors chemistry course. So we're learning a lot, some of the same things. You guys are going to learn a lot of new stuff, by the way, too, but it's good that we're able to transition back here, kind of hopefully recalling some of the things that we hopefully already learned. But I do want to go over moles again because it's such a key fundamental concept in chemistry. So we'll start with like a hydrogen atom, and we got theoretically, what's the weight of a hydrogen atom? Normally I'd say look at your periodic table, and in fact you had a periodic table, you look on the molar mass and you'd see it's 1 AMU. So 1 atomic mass unit. It's theoretical because it's not like we could take a hydrogen atom and then put it on a scale and it reads 1 AMU. It's not going to happen. But okay, so now we want to, let's say I get a pile of hydrogen atoms, and I want to get a practical weight. You guys should know what's a practical unit that you could use. You guys should know it would be grams. So let's say I get enough hydrogen atoms. Remember, they're so small, you can't measure a single one. I get enough hydrogen atoms that a scale can actually practically measure it in grams, and I get enough hydrogen atoms so that I weigh out 1 gram. So I have a 1 gram pile of hydrogen atoms, just kind of, hypothetically. Obviously, you're not going to have a pile because they're hydrogen atoms. Plus, they're all diatomic, so they're existing as a H2 gas. But theoretically, work with me. Let's say we get oxygen. Once again, I ask you, what's the theoretical weight of oxygen? You should be able to look at a periodic table and tell me it's 16 AMU. Let's say I get the same amount of oxygen atoms here as I had hydrogen atoms here. Question is, what would that pile of oxygen atoms weigh? Well, you guessed correctly, 16 grams, because wouldn't that make sense? If each oxygen atom is 16 times heavier than a hydrogen atom, I have the same amount of oxygen atoms as I have hydrogen atoms, so shouldn't my pile be 16 times heavier? Makes sense. Nitrogen, what's the theoretical weight of nitrogen? You look on the periodic table, it's 14 AMU. Get the same amount, what would that pile weigh? You guessed it correctly, it's 14 grams, and I can do the same with carbon and so forth. Okay, so question might be, I would, if I was going slower, trying to get you guys to be thinking, I would ask, well, somebody actually might ask, I think a key question might be, well, how much is in a pile? Because you guys understand, this is significant here, because whatever this is, that's a value such that the practical weight is always equivalent to the theoretical weight. And remember, that's a certain number. What do we call that number? You guessed it, that's what's called a mole. So the mole is the number of atoms or molecules needed such that the practical gram weights are equivalent to the theoretical AMU weights. Okay? And you guys, and then we utilize this concept in stoichiometry once again to predict the amount of products, for example, that we might produce in a chemical reaction. So now what's a mole? We can call it a chemist's dozen. Basically, we call it a chemist's dozen because it's the value that we use that just makes everything easier to work with. And that number is 6.02 times 10 to the 23rd. So, for example, if I needed, somebody might ask, why is this the number that chemists use that is convenient? Wouldn't a more convenient number, obviously it's going to be a big value because atoms are so small and we're dealing with such large amounts of atoms in even the smallest bits of matter. But why is this number so significant? Because I could ask you, let's say if you wanted 6.02 times 10 to the 23rd atoms of carbon, how much carbon would you have to measure out? Well, what you would say is, oh, if that's how many, that's a mole, and that's how many atoms of carbon are in a mole, and the mole is equivalent to the theoretical AMU weight. So I look up on a periodic table and I see the AMU weight of carbon is 12 AMU. Well, it's this many atoms that would make it equivalent to 12 grams, so it would be 12 grams I would measure out. So anyways, we can see obviously the benefit of scientific notation, so I don't have to write that out. The whole point is it's an extremely large number. So by definition, we're going to use that term molar mass. That's what instead of saying the AMU weight or molecular weight, molar mass would be the preferable unit to use. And this is what you guys want to become very familiar with, grams per mole. So we'll do a practice. This should look a little familiar to you guys if you've already had me before, a little roadmap. This is what we should be able to convert pretty easily between. Let's say we had the weight of something, or we wanted to convert between the weight of something and the moles of something. What would we use? We'd use what's called the molar mass. And then I'll give you a hint. You use the periodic table. We'll do a practice one, so in case I'm losing you. Question is, what's the link between number of molecules or atoms and moles? You guessed it, the value of a mole. 1 mole is 6.02 times 10 to the 23rd. So knowing this will allow us to convert between these. And then the last thing is, when we're dealing with gases, and this is at STP, standard temperature and pressure, here's an equivalency. You know, I'll bring that up. I'll just remind you guys, so what we're saying here is if you had 1 mole of a gas under at standard temperature and pressure, it's going to occupy a space that's 22.4 liters. So that's this size right here, so it helps to know that conversion factor. Okay, want to practice one for you guys here real quick. So let's just do this. Let's say I want to know if I had 3.01 times 10 to the 23rd molecules of, let's say, carbon dioxide. I want to know what does it weigh? How many grams would that be? Okay, so here's how you would use the little roadmap, right? So you guys remember we use unit analysis. What do I want to find? I want to know how many grams of carbon dioxide do I have? Okay, and then you guys remember the end point, and then you do the start point. Well, what information do I give you to start with? Oh, I start with the fact that I have 3.01 times 10 to the 23rd molecules of carbon dioxide, okay? So, I just use my map. You guys see where on my map am I starting? You guessed it, down here at the bottom. And where on my map am I going? Grams of carbon dioxide. I'm going to the weight. So you guys see, I'm going from here. And you guys see, all roads lead to moles. That's why moles is so important. I'm going to first convert it to moles, and then I'm going to use the molecular weight to ultimately convert it to weight in grams. So you guys see, it's 2 roads on this journey. So then I would proceed to do 2 sets of parentheses. First parentheses, I'm going to convert from number of molecules to moles. Well, you guys got to look. Molecules is on top, so what do I want to put on the bottom? I want to put the molecules on the bottom. So I have 6.02 times 10 to the 23rd molecules is equivalent to 1 mole on top. And you guys, what I would highly encourage you guys to do is cancel out units as you're going along. Molecules cancels out. And you guys see, hopefully you can see, I don't know. You see the unit that's left is moles. So now I'm at moles. Last thing I got to do is convert it to grams. So how do I go from moles to grams? Once again, use the molecular weight, otherwise known as the molar mass. What do? I look at the periodic table. I see that the mass of carbon is 12. I see that the mass of oxygen is 16, but I have 2 oxygen atoms. 16 and 16 is 32, plus the 12 from carbon is 44. What do I say? It's 44. You guys remember how to say it? We say it's 44 grams per mole. What that means is, if I have 1 mole of carbon dioxide, it's going to weigh 44 grams. So that's my conversion factor. So I have mole on top. What do I want to put on the bottom? Remember, it's always per 1 mole. So I'm going to put the 1 mole on the bottom, and that's equivalent to 44 grams on top. And then you guys see, if you do it right, the only unit left standing is the grams, which is right here. Once again, what do? I multiply all the numbers on top, and I divide all the numbers on the bottom. This is actually pretty easy. I try to use numbers that were easy. Hopefully you guys can see 3.01 times 10 to the 23rd divided by 6.02 times 10 to the 23rd. That's 1/2. So then it's just 1/2 of 44. So the answer would be 22 grams. That's how much 3.01 times 10 to the 23rd molecules. That's a huge amount of molecules, and yet it only weighs 22 grams, which doesn't weigh too much, like 22 kilograms. Okay, moving on, guys. I'm gonna take all week to get our spring cleaning done. This dude's done already. I think she's slightly more clean than he is. Slightly more organized. Hopefully guys, we're not like that. Okay, last one guys. Promise this is it. But this is a good one. Hopefully you guys see the value in this. Okay, so here's the question. It says, the compound para-aminobenzoic acid, also known as PABA. I don't know if you guys ever look at labels on things that you buy, but I don't know, I'm kind of a chemistry teacher, so obviously that interests me. I'm hoping it starts interesting you. But you might see PABA, that's a kind of a common, at least it had been, I don't know if they've since outlawed it, I don't know if it causes any problems, but last time I've checked, they've had PABA in sunscreen. So anyways, you can take that compound PABA in sunscreen, and you can break it down so chemists can analyze it, right? To analyze it means to see what is it made up of, right? So they take PABA, they take a sample of PABA and they break it down, and they find that 61.31% of the PABA by weight is carbon, 5.14% is hydrogen, 10.21 is nitrogen, and 23.33% is oxygen, okay? So we find that out. The question is, what's the empirical, you guys, once again, empirical, fancy word for tested. It's a formula that's determined via testing. What is the empirical formula of PABA? Basically like the chemical formula. Like I'd ask you what's the chemical formula of water, you'd say it's H2O. Now the empirical formula, you guys remember, is the smallest whole number ratio. It could be different, the true molecular formula, but nonetheless, this would be the formula showing us the ratio of atoms. Okay, so here's how you would do a problem like this. Okay, this could be like on an AP test. What's the empirical formula? What I would say is you kind of have to try to think, okay, how would I tackle this first? Normally, if we were in class, I'd leave a lot of time for you guys, and then I'd ask you guys to because I always like when you guys can kind of figure out the problem solving. A lot of times, the brilliant people in AP chemistry, you guys kind of figure it out, and I just kind of lead you. But just for sake of time, we're just going to go. So you have to think. You just have a sample of PABA. Just this big. Sample of PABA, that they put in the sunscreen. The question is, what do you guys think if you had to theoretically have a certain amount of this material? What would be a good theoretical amount? Just kind of looking at the information we have here, how much PABA do you guys think? What would make our life a lot easier if we imagine we had how much PABA? I'm hoping you guys are thinking, well, they give us percentages. Percents have to do with the number 100. I'm thinking maybe you just assume you have 100 grams of this stuff. Now you guys look, you're going to see why this is easy. Because if I have 100 grams of this stuff, how much carbon do I have? Yeah, you can guess it. If there's 61.31% is carbon, then I must have 61.31 grams of carbon. And how much hydrogen? I must have 5.14 grams of hydrogen, 10.21 grams of nitrogen, and 23.3 grams of oxygen. Okay, so at this point, would I say my formula is carbon 61.31, hydrogen 5.14? Does that sound right? It shouldn't. You know why? Because when you guys are doing a formula, it's not a ratio of weights. What is it? It's a ratio of number of atoms. So the masses here isn't going to help me. So what do you guys think we might want to convert the masses to, which might help give us an indication of how many atoms are there? You guessed it, moles. And you guys should know, it's not difficult to convert to moles. Remember, I used the molar mass. What's the molar mass of carbon? It's 12 grams per mole. What's the molar mass of hydrogen? 1 gram per mole. Nitrogen, you guys would look at your periodic table. It's, you guys see I'm putting the grams on the bottom because grams on top. It's 14 grams per mole. And oxygen was 16, if you guys remember from just before, okay? So then, I do my math. Right, grams cancels, and I'm going this divided by this divided by that, and so forth. I think I already did it before. I'm going to get something like 5.105, something like that. I'm going to get here, it's 5.14. Here it is 0.73, I believe. And here it's 1.46, something like that. Okay, and that would be moles of carbon, moles of hydrogen, moles of nitrogen, and moles of oxygen. So somebody might say, oh, well, so Mr. Wilson, is it carbon 5.105, and hydrogen 5.14, and then nitrogen 0.73, and then oxygen 1.46. You guys technically, that is actually the ratio of atoms. That actually is. That's what we, when we get moles, moles is the number. But you guys know, this should look funky to you. You guys know no chemical formula we're going to have. You can't have parts of atoms, right? It has to be a whole number. So the question I have for you guys, and some of you guys who are more mathematically inclined, I'm hoping you guys pause it right after I ask the question. You guys try to figure out before I just tell you right away. How can I keep the same ratio here and yet get whole numbers? What could I do? So I keep the same ratio because the ratio is correct, but I can't have non-whole numbers in my formula. What you guys should know, whatever you do to one, as long as you do it to all, you're going to keep the same ratio. So what I would recommend is you take the smallest number and just divide by it. But once again, if I'm going to keep the same ratio, I got to do everyone by the same thing. So I'm going to divide everyone by 0.73. When you do that, you're going to get, and you know what, you're going to get about, and I say about because it's not going to be exact. You know what that's due to? That's due to experimental error. When you get these percentages, it's going to be slightly off, and so then, therefore, it's not expected that these aren't. But what you're going to find is you should get something very close to a whole number, and when you do that, you're going to get about 7 here. You're going to get about, what was it? Oh yeah, you're going to get about 7 here, right? You're going to obviously get 1 here because that was the smallest number that I divided by. And then there, 1.46 divided by 0.73, you guys can probably figure it out. 2. And so now we have whole number. And so what we would have is, I would say this is C7, H7, nitrogen's just 1, so I just put an N, and then it's O2. That would be the empirical formula of power. All right, guys, I believe that is it. That is, we will see you guys next time.